Hey everyone, and welcome. So today we are diving into a material that a lot of people are calling the key to the next solar energy revolution. Seriously, it promises to make solar power way more efficient. We're talking about potentially doubling the output of every single panel. Let's get right into it.
So the big question we're really asking today is this. Is the solar tech we see on rooftops and in fields everywhere about to get a huge, massive upgrade? Well, the answer just might lie in this one material with a pretty cool name, Perovskite.
Okay, to get why this is such a big deal, we need a little context. I mean, solar power is already a massive success story, right? It's one of the cheapest new sources of electricity out there, and it's growing like crazy, by an incredible 29% in 2024 alone. But there's a catch. It's starting to hit a wall.
And this is that wall. You see, the regular silicon panels that are everywhere today, they have a practical efficiency limit of about 23%. So what does that mean? It means they can only turn about a quarter of the sunlight that hits them into electricity. And look, if we're serious about decarbonizing the planet, we've got to do better than that.
All right, so here's our game plan for this explainer. First up, we're going to look at why we even need a revolution in the first place. Then we'll meet our so-called wonder material. After that, we'll dig into the Perovskite paradox, the massive potential versus some very real challenges. We'll see how it's making the jump from the lab to the real world. And finally, we'll dream a little about how it could power our future.
Okay, let's kick things off. Section 1. Solar's next revolution. So really, why do we need to look past the good old silicon technology that's actually served us so well for so long? All right, let's introduce the star of the show, Perovskite. So what is it? Well, the name refers to a whole class of synthetic materials that have a very specific crystal structure. And here's the crucial part. They're made from cheap, abundant stuff like lead and tin. So no, this isn't some super rare exotic element you have to mine from a meteor.
And that brings us right into Section 2, Meet the Wonder Material. Let's get into the secret sauce, how this stuff could help us completely shatter those solar limits we were just talking about.
Okay, so the truly brilliant idea here isn't to get rid of silicon, it's to have them team up. It's called a tandem cell. Just picture this. A super thin layer of perovskite is basically sprayed on top of a normal silicon cell. Now that perovskite layer, it's amazing at grabbing the high-energy blue light. But the light it doesn't catch, the lower-energy red light, just passes right through to the silicon layer underneath, and silicon is great at capturing that. It's literally a 2-for-1 deal, squeezing way more power from the exact same sunbeam.
And the result? It is absolutely staggering. Remember, silicon alone maxes out around 23%. But when you pair it with perovskite, the theoretical max efficiency leaps to over 47%. We are talking about potentially doubling the power output. Just think about that. You could power twice as many homes from the same solar farm, or get the same amount of power using half the land. That's not just an improvement, it's a monumental leap. So you're probably wondering, hey, if this is so great, why haven't we been doing this for years? And that's a great question. As David Ward, the CEO of Oxford PV, points out, the idea of tandem cells isn't new at all. The problem was that the materials you needed were just way too expensive to be practical. But perovskite, it's different. Because it's made from cheap materials, it makes this incredible idea actually affordable for the first time ever. Which, of course, brings us to Section 3, the Perovskite paradox. Because let's be real, with any tech that sounds this good, there are always going to be some hurdles, right? This is where that massive potential smacks right into some very serious challenges. So here's the paradox in a nutshell. On the one hand, you've got this amazing promise, a brand new kind of panel with way higher efficiency made from cheap stuff. Awesome. But on the other hand, you have the tough reality. Early versions just weren't very durable. They would break down in heat and moisture, and they contained small amounts of lead, which, as we know, is toxic. Okay, let's tackle that lead issue head-on, because it's important. According to researchers like Joseph Barry over at the National Renewable Energy Lab, context is everything here. First, the amount of lead is tiny. And get this, it's way less than the lead that gets spewed into the air from burning coal to get the same amount of energy. Plus, the industry is already figuring out recycling processes to handle it safely when the panel is done. But that other point, durability, that is the real billion-dollar question. I mean, silicon panels come with 30-year guarantees. Why? Because we have decades of data from panels out in the real world proving they last. So how on earth does a brand new material prove it can hang tough for 30 years? This, right here, is the central challenge that companies are racing to solve.
So how are they proving it can last? Well, that takes us right to Section 4, from lab to reality. Let's see how scientists are tackling this exact challenge as we speak.
Yeah, they obviously can't wait 30 years, so they do the next best thing. They basically torture them. They stick these cells into special chambers and just blast them with crazy heat, intense humidity, and wild temperature swings. These are called accelerated aging tests, and they simulate years and years of wear and tear in just a few months or even weeks. And that's how they get the data they need to feel confident this stuff will last.
And you know what? The progress is happening incredibly fast.
Seriously, new efficiency records are making headlines all the time. A Chinese company called Longji just recently hit a mind-blowing 33.9% for a small lab-scale cell. That is way past silicon's limit, and it's starting to creep closer and closer to that theoretical max we talked about.
But hold on, we have to be a little careful with those big headline numbers. As one of the pioneers in this field, Tsutomu Miyasaka points out, these lab records are for what they call champion cells. Think of them as the best of the best made under absolutely perfect lab conditions. It's a whole other ballgame to keep that same quality when you're mass-producing giant panels in a factory. So the real test is what these companies can actually sell to people.
And speaking of that, things are definitely moving. This isn't just theory anymore, not by a long shot. Oxford PV has already sent a pilot batch of panels with 24.5% efficiency to a solar farm in the US to be tested. Kalox has actually made its first commercial shipment. And Swift Solar, they're putting their panels on telecom towers. The technology is officially out in the wild.
All right, this brings us to our final section, and it's a fun one, powering the future. So let's say they solve this durability puzzle. Where could this technology actually take us?
This is where it gets really, really cool. Because perovskites are so efficient and can be made super thin and flexible, we could start seeing them in all kinds of new places. I mean, imagine putting them on the roof of your electric car to give it a constant trickle charge, just to get a little extra range. Or using them to power a whole new generation of cheaper satellites in space. And get this, some companies are even working on transparent versions. You could literally turn the windows of a skyscraper into a giant invisible power plant.
And the people leading the charge here, they are not shy about their predictions. Scott Grable, the CEO of Kalox, he puts it very simply. He believes this shift isn't just possible, it's inevitable, and that the impact will be, in his words, utterly transformational.
Which leaves us with the big, final question, right? We've seen the incredible potential in the lab. We're seeing those very first baby steps into the real world. So now the key is to just watch those pilot projects. Is the real-world data on durability and performance finally going to prove the promise of this wonder material? You know, the next few years are going to be absolutely fascinating to watch. This is one to keep an eye on for sure.